Chapter 21 is the second part of confidence intervals for percentages. So we figured out how to find a 95% confidence interval. We just do our sample percentage plus or minus 2 standard errors. But what if we wanted to say find a 90% or a 99% confidence interval? So those are both very common confidence intervals as well that we'll want to be able to find. So in general, the formula for the confidence interval is actually sample percentage plus or minus this z star times the standard error. So if it's 95%, then z star is 2. But we might want to find z star for other confidence levels. The way we'll do this is with the normal table, so let's try one. So if I want to find an 80% confidence interval, the idea is that if you draw the normal curve, you want 80% in the middle. Because you're taking 80% of the most common values, and then the tails are kind of the more extreme, but you want 80% of the middle. And then you say, okay, if there's 80% in the middle, then 100% minus 80% equals 20%. And 20% divided by 2 is 10%. The reason why is that your total area always has to add up to 100%. So there's 80% in the middle, there's 20% left over. But you have 2 tails, so you have to divide it by 2, and that means there's 10% left to go in either tail. And then we're looking for z star, which is this value right here that breaks up our curve into these areas. There's a couple different ways you can look this up. I could look up 10%. The reason I look up 10% is that the area on your table is always the area to the left. So let's pull up our normal table. We're looking for the z value that has 10% to the left. That would give me this line right here. So 10% of area to the left. Remember, we're not going to find it exactly, we're just looking for closest. And I think this one would be closest, 9.68%, z is negative 1.30. So this is negative 1.30. Now due to symmetry, z star would be equal to positive 1.30. So my final answer is z star equals 1.3. Now if you want, you could try and look up this line right here for the positive z value. And you'd say, okay, there's 10% to the right, that means there's 90% to the left, or 10% plus 80% means that the total area from here all the way over is 90%. So I can go to my normal table and look up 90%, and it looks like the closest one is this positive z equals 1.30. So in any case, when we're done, z equals 1.30, z star. Okay, now we want a 90% confidence interval. So here's my 90%. So how much is left over? So there's 10% for both tails, which means 5% for each tail. So here's my 5%, here's 5%, and now I need to look up and figure out what the z star value is using my normal table. Well, from here all the way over is actually 95% because you have 5% and 90%. So I go to my normal table and I look up 95%. The closest is this 1.65, so z star equals 1.65. So that's my answer there. For 99%, there's 1% left over. And divide that by 2 is 0.5% for each tail. So 0.5%, 0.5%, and we're looking for z star. So I can go to my normal table, and let's say we want to find this value right here. The area to the left is 0.5%. So 0.5 as a percentage, it looks like this closest one is z equals negative 2.60. So this is negative 2.60. So by symmetry, z star is positive 2.60. Or just 2.6. In example 228, a health inspector takes a random sample of 310-year-olds in a city and finds that 73% of them have had chickenpox. So number one, what is your estimate for the percentage of all the 10-year-olds in the city who have had chickenpox? So we don't know what percentage of all the 10-year-olds in the city have had chickenpox, but in our sample, 73% of them have had chickenpox. So we're going to use our sample percentage is 73%. So our estimate of the population percentage is 73%. So that's our estimate for all the children that have had chickenpox. And part 2, your estimate is likely to be off by how much? So that's asking, find the standard error. Let's see, we have a sample of 300 people, so my sample size equals 300, and my sample percentage equals 73%. Now the formula for standard error for percentage is the square root of your population percent times 100 minus the population percent divided by the sample size. Now, I don't know exactly what my population percentage is. Instead, I have to estimate my population percentage, which means that this is just going to be approximate. So I use the sample percentage instead of the population percentage. Over the sample size. So this is going to be 73 times 100 minus 73 divided by 300. Which is 2.56%. So just a couple notes. So once again, we have to estimate the population percentage with the sample percentage, which means that my standard error isn't actually exactly correct, it is just an estimate. And then my final answer is the estimate is likely to be off by about 2.56%, since that was my standard error. Now part 3, find a 90% confidence interval for the percentage of 10-year-olds in the city who have had chickenpox. So once again, we want a 90% confidence interval. So you could look at the previous page and see what we figured out for z star for 90%, or we could calculate it again. So if there's 90% in the middle, there's 10% left over, which means 5% for each tail. And I'm looking for z star. So I'm going to look up 5% to the left. And 5% to the left gives me this negative 1.65. So if this is negative 1.65, then z star equals positive 1.65. So now I can calculate my confidence interval. The formula is sample percentage plus or minus z star times the standard error for your percentage. My sample percentage was 73%. Plus or minus z star, which is 1.65, which we calculated over here, times the standard error, which we calculated in the previous part, so 2.56%. if I do my multiplication first, then I have 73% plus or minus 4.224%. When I subtract, I get 68.776%. When I add, I get 77.224%. And every single time you find a confidence interval in this class, you should write the interpretation for me. So, we are 90% confident that the percentage of all the 10-year-old kids in the city who have had chickenpox is between 68.776% to 77.224%. So I don't know exactly what the population percentage is, but I feel 90% confident that it's somewhere between the 68 and the 77%. Example 229 is in here because it's a common misconception, a common question people miss on the test. It says a person took a simple random sample from a large university. The percentage of women in the sample was 54.3%. The 95% confidence interval for the percentage of females for the entire university is 51.1% to 57.5%. So the first question is true or false? There is a 95% chance that the sample percentage is between 51.1 and 57.5%. So this is false. And there's actually a couple things wrong with it, but the first one, the main one, is that the sample percentage is 54.3%. Because you took the sample, you know the sample percentage. So there is a 95% chance that the sample percentage is between 51.1 and 57.5. You absolutely know that it is between those numbers because you know what it is. And that's always going to be true. You're always going to know what the sample data is because you've taken the sample. That's what you base the confidence interval on. So this would be false. So now we have some remarks. The first one is that these confidence intervals are valid, basically meaning, yes, we can use the normal curve. And when did we use the normal curve? To find z star. It's valid if the number of draws is large enough. For percentages, the number of draws is considered large enough if the sample size times the sample percentage is at least 1,000, and the sample size times 100 minus the sample percentage is at least 1,000. However, for this class, I'm not going to make you check to see if the number of draws is large enough. We'll just assume that it is. Okay, a couple more remarks. 231 is when reasoning forward, like from the box to the draws, or in other words, from the population to the sample, we use probabilities, meaning chances. So if you know information about the population and you want to figure out information about the sample, you can use what we call probabilities or chances. When you reason backwards, when you're going from the draws to the box, that means from the sample to the population, we don't talk about probabilities anymore, we talk about confidence intervals. So once again, probabilities are for when you're going from population to sample. Confidence intervals are for when you're going from the sample to the population. Next remark, the methods in this chapter only apply to simple random samples. And finally, increasing the sample size improves your estimate. So, if everything else is equal, as your sample size increases, then your confidence interval gets shorter. And when it's shorter confidence intervals, that means it is more precise. And more precise is a good thing. So we'll do a smiley face. In this next example, suppose we have a box containing a very large number of marbles, 80% are red and 20% are blue. So this is a huge box, that's our entire population. So we take 100 samples of 2,500 marbles each. That's a very big sample. And construct a 95% confidence interval for each sample. Now, because we're doing a 95% confidence interval, we know that about 95% of the intervals will include the true value. So here's a simulation. You can see the 80% is the true percentage of red. We have our population percentage equals 80%. And most of these confidence intervals are containing it, but not all. So like this one misses it. There's two here that miss it. And this one misses it. I think that's all of the ones that miss it that I can see just quickly here. So, just as our notes, remember, what does a 95% confidence interval mean? So, 95% confidence means that of all the possible confidence intervals, about, not exactly, but about 95% will contain the true population percentage. So once again, this is what a 95% confidence interval means. Now, let's go through two common interpretations. This first one is incorrect. Well, it's written correctly here, but this is a very common misconception. Do not put this one on the test. Okay. So what people like to say is they want to try and say that there's a 95% chance that the population parameter is in the interval. So they want to say there's a 95% chance that my population percentage is within the interval that I find. You cannot say that. So this first one is very common misconception. Do not use this misconception. Okay, this is why it's wrong. This is why you can't say that. The reason why is the population parameter or percentage is fixed. We don't know what it is, but it's not changing. So I might not know what percentage of red marbles there are, but if I counted them all, I would be able to find the true population percentage. It's not variable, it's not changing, it's a fixed value. Okay. And the population percentage is not random in any way. So it doesn't make sense to talk about a chance for something that's not changing. Okay. So that's why this misconception is wrong. Okay. So what does it mean? The 95% confidence interval means of all the samples we could have chosen, 95% of the resulting confidence intervals would cover the population parameter, or in our case, the population percentage. So this is the correct meaning. Or in other words, if we use this process many, many times, we would be right about 95% of the time. This next one is an activity that I did with the previous class. So in this previous class, we wanted to estimate the percentage of Earth that is made up of land versus water. And so we took a sample of 10 points on the Earth, and we calculated the percentage of points that were land. So basically, they tossed the globe up in the air, caught it, and had a specific point on their finger, and wherever that point was, they decided if it was land or ocean. So one group got land on 7 out of 20 tosses. So for this specific group, what was their percentage? Their percentage would be the 7 out of 20 times 100%, which is 35%. So was this number a population parameter or a sample statistic? This would be a sample statistic because they didn't do it for all possible points on the globe. They just took a sample of 10 points. Oh, apparently 20 points. Number 3, calculate a 90% confidence interval for the percentage of land. So once again, for a 90% confidence interval, that means I want 90% in the middle, 10% left over for both tails, or 5% in each tail. Now this time I'm going to say I want to find this line, just because there's multiple ways you can do it. Let's say I want to find this line. The area, all the area to the left actually adds up to 95%. So go to the normal table, make sure you look up 95%, which gives me the positive 1.65. So Z star equals 1.65. Let's see, what else do we need to find? We also need to find the standard error. The standard error for my percentage is the square root of your population percent times 100 minus your population percentage divided by your sample size. And this is going to be approximately equal to I'm going to use my sample percentage. So 35 times 100 minus 35 divided by my sample size of 10. Sorry, 20. They did 20 tosses. 20 tosses. Which is 10.66%. Now, let's find our actual confidence interval. So it's always our estimate, which in this case is our sample percentage, plus or minus Z star times the standard error, or your percentage. So my sample percentage was 35%, plus or minus Z star, which is 1.65, times the standard error of 10.66%. And this gives me 17.41% to 52.59%. So they are 90%, just 90% confident that the true percentage of land on the entire Earth is somewhere between 17 and 52%. Now, number 4, is there any way to know if this group's confidence interval actually covers the true percentage of land? No. They are 90% confident that the true percentage is between 17.41 and 52.49%. Okay. But, unfortunately, there is no way to know if your interval actually contains the true percentage. So I do say unfortunately, it is very unfortunate. It's kind of a pain, and one thing that sometimes people don't like about statistics. And here's the reason why. So several groups did the globe tossing activity, and we ended up with 20 results and hence 20 confidence intervals. So they each tossed it 20 times. Here's the number of times it landed on land. So like 7, 6, 7, 5, 11, 10, etc. And so then they calculated the percentage of land. Some people had 35%, 25%. Some people were all the way up to 70%. Obviously, there's a lot of variation here, right? And part of this is just poor sampling because they were just tossing the globe up in the air, that we weren't extremely accurate here. But they all calculated their standard error. Notice it's slightly different depending on what sample percentage they got. And then they calculated a 90% confidence interval. And notice that these all change a bit. So like 17 to 52, 9 to 41, 26 to 63. So if they're all getting different confidence intervals, how do they know if their confidence interval contains the true percentage? And the answer is they don't. Unfortunately, they just don't. So, did each group get the same number of land results? No. Did they each get the same percentage of land? No. And they didn't get the same confidence interval either. Now, scientists have discovered that the true percentage of land is really 29.2%. So is this 29.2 a parameter or a statistic? It would be a parameter because it's for the entire population, so it's a parameter. Okay, and our next question is, did all of our confidence intervals contain the true value of 29.2%? Let's go back up and look at them again. So we're looking for 29.2. So yes, 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 no. Let's see, yes, yes, no. Yes, 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 no. Yes, yes, yes. So we had 3 confidence intervals that didn't contain my population parameter, right, or my population percentage. So no, 3 out of 20 didn't contain the population percentage. Which means how many of the confidence intervals actually did contain the true percentage? If 3 didn't, then 17 out of 20, which is 85%, actually covered the true percentage. So here's our little diagram, so you can see. So I drew in each of the confidence intervals, and these red ones are the ones that didn't contain the true value of 29.2%. So we were doing a 90% confidence interval. So let's just make ourselves a note. So we found 90, oh wait, now I forgot. For sure, let's see. Yes, we did. We found 90% confidence intervals. So we would expect about 90% to contain the true percentage. And in this scenario, we only had 85%. The reason why is we only did it 20 times. We only had 20 confidence intervals. We technically said 90% out of all the possible confidence intervals. So here's the results for 150 simulated confidence intervals. So you can see all of our confidence intervals. The red ones are the ones that don't contain the true value. And out of these 150 confidence intervals, 90% of them contain the true percentage of 29.2%. So, once again, why do you think we say that it's a 90% confidence interval? Because of all the possible confidence intervals. Actually, let's go back even a little bit further. So because out of all the possible samples, 90% of the resulting confidence intervals would actually contain the true population percentage. Or in other words, or if you kind of want it in plain language, if you prefer, what does it boil down to? If you use this method, you will be accurate 90% of the time. Notice this doesn't say you have a 90% chance to be accurate. It's if you do it many, many times, overall you'll be accurate 90% of the time. But for one specific try, we don't know if you're going to be accurate or not. And now we're just going to practice 2 problems. Okay, a researcher in Utah takes a simple random sample of 200 high school students. So my sample size equals 200. And 69% plan to go to college. So my sample percentage equals 69%. Find a 99% confidence interval for the percentage of all the high school students who plan to go to college. Let's see, so I do need to figure out what my Z star is. So if we want 99% in the middle, then that means there's 1% left over. 100 minus 99 is 1. And then divide that by 2 because you have 2 tails, gives us 0.5% for each side. If I look up just this left side right here, the 0.5%, the closest I can get is Z star equals negative 2.60. So negative 2.60, so Z star equals positive 2.60. And I need to find my standard error, which is equal to the square root of your population percentage times 100% minus your population percentage over the sample size. Which is going to be about, so we're going to actually have to estimate that with our sample percentage of 69. So 69 times 100 minus 69 divided by our sample size of 200, which gives me 3.27%. So I estimate that there's 69% of all the high school students, seniors who plan to go to college, give or take about 3.27%. But let's go a step further. Let's find our actual confidence interval. So it's going to be your estimate, which in our case is sample percentage, plus or minus Z star times the standard error. Our sample percentage is 69, plus or minus Z star, which is 2.60, times our standard error of 3.27. If I do the subtract first, so 69 minus 2.6 times 3.27. If I subtract first, I get 60.498. And then if I add, I get 77.502. So that is my 99% confidence interval. And we can interpret it as we are 99% confident that the true percentage of all high school seniors in Utah, since I only talked about Utah, that plan to go to college is between 60.498% and 77.502%. Now for our next example, in a certain city there are 100,000 people aged 18 to 24. A simple random sample of 500 is drawn, of whom 194 turn out to be currently enrolled in college. So let's make your note. Our sample size equals 500. They took a simple round sample of 500. Let's see, estimate the percentage of all people who are in the city who are currently enrolled in college. So our best estimate of the population percentage is the sample percentage. And our sample percentage is 194 out of our sample size of 500. Don't forget to times it by 100% to change it into a percentage. So 194 divided by 500 times 100% gives me 38.8%. In part 2, put a give or take number on your estimate. In other words, find the standard error. So our standard error for our percentage is equal to the square root. So we're going to do our sample percentage. I'm going to do an approximate because I have to estimate my population percentage with my sample percentage. So 38.8% times 100 minus 38.8% divided by my sample size of 500, which is 2.18%. So what does this mean? We estimate that the population percentage is 38.8%, give or take 2.18% or so. So that tells you how much you're likely to be off. But if we want to have even more confidence, we can find a 95% confidence interval. So remember, for 95%, Z star equals 1.96. Sorry, equals 2. .96 is actually a more accurate result. But in our textbook, we've always said 2 standard errors has a 95% because we rounded it to make it easy to remember. And so we'll continue to just use 2, even though 1.96 is slightly more accurate. Okay, let's see. I think we've found everything we need. We just need to actually calculate it. So it's always your estimate, which is our sample percentage, plus or minus Z star times your standard error. Our sample percentage is 38.8%, plus or minus 2 times our standard error, which is 2.18%. So in my calculator, I'll do 38.8 minus 2 times 2.18. So that gives me 34.44%, 2, and now I'll do the same thing, but I just change the minus to an add. 43.16%. That is my 95% confidence interval. And we can write our interpretation. So it's for this certain city. So we are 95% confident that in this city, the true percentage of all the 18 to 24-year-olds who are enrolled in college is between 34.44% and 43.16%.